My name is Darren Croton. I'm a professor at Swinburne University in Melbourne, Australia. My main area of research is galaxy formation models. And we've heard a lot about simulations and models and galaxies and so on so far. So what I actually want to do is fill in some detail about how we build synthetic universes, and then I'll tie that to a few other things which I'll mention in a minute. But before I do, I actually want to get a show of hands of how many astronomers do we have here? So how many people who consider themselves an astronomer? Right?
Definition of astronomer.
You can define it any way you want.
Well, somebody who's looked at a lot of astronomical
Yeah.
data.
So how many non-astronomers do we have here? Right. Good. Because
But actually, the other interesting question is how many people are there who didn't raise their hand for either one?
yeah, so how many none of the above? It's a binary question though, unfortunately. So none of the above means there was a bit of confusion. All right, so we do have some people here who are not astronomers, and my guess is that a lot of this terminology and stuff like that is kind of going a little bit, and you're looking for the bigger picture, and so we're filling that in as well. And this is an AstroInformatics workshop, not necessarily a galaxy formation workshop. The focus is on that mainly because this is a huge area in astronomy where people are taking this data and putting it up into the cloud and all that sort of stuff. So that's why the focus is on that, and people want to use that data and use it correctly. But so I want to sort of bring it back a bit so that even the non-astronomers and the non-experts in this particular area, I'm hoping that you'll get what we do, so that when the astronomers go to conferences and they hear someone say mock catalog, semi-analytic model, go to this link or something, you'll have some appreciation of what it is that we're talking about. So I want the lights on. I think when the lights are down, it becomes a bit gloomy and we all just sort of jump into our email. But this movie that's running in the background, is it simulation or real data? If you know, don't say. Well, so real data or simulation? Simulation, we have simulation. Simulation. Hybrid. No, it's real data. This is the 2DF Galaxy survey. Okay, and it's a bit deceptive. When you see movies like this, you have to make the galaxies 100 times larger, otherwise you wouldn't see them. That's how empty space is. So it's not really real in that sense. And what they have done is the 2DF survey didn't have the wonderful data that we're getting from the surveys that are going on now. It was essentially just positions on the sky and then one or two filters. So what they did was they color matched those galaxies to HST galaxies to make it look nice. But this is real data, right? And it's interesting that we can't tell the difference anymore. At least we're uncertain about committing. So that does say that even though the models have a lot of challenges, often it's not that obvious what we're actually working with. So here's a breakdown. I have 3 lectures. This is my first one. So here's a breakdown of what I want to cover. So in this first one, it's all about building synthetic universes. So I'm going to take you through the steps to build a galaxy formation model. So you will understand at the end of this how to build a galaxy. Okay? And I'll do it in a way that I'm hoping you will understand. And if you don't, please stop me and ask. Because even though it's insanely complex, you can break it down into simple steps, and that's what we do. In the second part, second talk, which is tomorrow, I'll take it another level, and we're going to move into code. And so what I want to do is show you how we actually implement that in code, the parameters that we use, what they mean, what their uncertainties are, because in the lab, which is tomorrow afternoon, you're going to download and run a semi-analytic code. This is the one that has built the mock catalogs that went into the Millennium Simulation database. So it's a very popular model. You're going to download that and run it with different assumptions about the physics. And so you see the differences that those assumptions make to a galaxy model. And then one of the outcomes of that is you'll have your own virtual universe. And in Herad's lab, you'll upload that universe into the database, and then you'll query it. So we're going to link some labs here. So you're going to build your own universe, and then you're going to, in other labs, you're going to actually manipulate in the database. And so I want you to understand what it is you've done, not just go and press a couple of buttons and tune some knobs and make a line go through some data points and say, I've done it, right? That's not the point. And then in my final talk, we'll see exactly what I focus on, because a lot's been covered already and there's still more days to come. But I want to talk about the universe in the cloud, and it's already been the focus of some of the talks, and I'll talk about our effort and some additional ideas about what the challenges, what data access and all this will be in the coming years, and how we do science. So here are the things that I really want you to take away. Okay, so the basics of galaxies and how they're built, right? So I want you to leave here understanding what we do. It's not a magic box. The uses and limitations is key. You know, Risa hit on this. This is one thing you remember from this whole meeting, remember that the questions are really what's the most important thing almost. You can have crappy methodology, crappy tools, whatever. As long as your questions are well posed and you interpret your results in relation to those questions, you're honest about it, you can often do great science with that. And then the challenge of data access and delivery. Taking all this and making it usable by people. So you're going to do a lab, you're going to build your own galaxy formation model. The model actually does reasonably well at redshift 0. So redshift 0 is the present day, our universe as we see it right here and right now. So galaxies in this virtual universe look good. As we go back in time, it gets worse. These galaxies don't match the data that we've measured. Now the data is not that great, but the galaxies do worse. And so I have a challenge. Okay? So we're going to break into groups of 3 when we do the lab. So you're going to work in teams, and you're going to run the model as a team. Okay? Now at redshift 1, which is when the universe was half its present age, so 8 billion years ago, you're going to plot the stellar. It's a statistic that we measure to quantify how many galaxies of a given mass there are in the universe. Okay? So the group that reproduces the observed stellar mass function will win an iTunes gift card to the value of $20. The group that does redshift 2 will get a $30 gift card. The group that does redshift 3 will get a $40 gift card. If your group does all of them, you get $90 in iTunes gift cards. Okay? Now, here's the catch. I don't have to give away a prize. It has to match the data, but I'm the judge of what's a good match. Okay? I understand how hard this is to do. And if you can't get a good match, win the prize, but that's fine. Okay? It's fine for me. All right? So that's number 1. Number 2, and this is the most important thing, you have to come up as a group and explain to me what you did to get that match. Not, oh, I changed this parameter by this amount, but changing this parameter caused more stars to form in low-mass galaxies and very early in the universe, which blah, 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 blah. Or I increased the supernova feedback, which changed. And we'll go into all these things in a minute about the different components of how to build galaxies and so on, and what it does, how it changes the evolution and so on. So you have to come up and say why. And so this is what I'm saying. If you just get a good match, but you have no idea why, you won't win the prize. So you have to think about what you're doing. We're not just tuning knobs here. Okay? All right, good? Who's up for it? Who wants to win a $90 of iTunes gift cards? That's 90 copies of Angry Birds, by the way. So the redshift 0 match still has to look reasonable. Okay, so it's important. Yeah, you can't just match it, and you have to explain what worked, right? And we're talking about the evolution of galaxies. But of course, redshift 0 match might get worse in matching that higher redshift. But that might be okay, because there are other things we can do at redshift 0 to fix that, and that won't be the focus. So you can't totally destroy the model just to get a fit at 1 redshift. Okay? That's not physical. Okay? But, you know, it can get a bit worse in places. So you can see that there's an increasing level of difficulty here, which is why there's a pay scale. All right, so let's get started. Galaxy formation primers. So I'm going to quickly some of the stuff that's been talked about already, just setting the groundwork and just reminding you, because I need to go over this stuff in order to build galaxies on top. So there's two parts to a semi-analytic model, or galaxy formation model as we build it. There's a skeleton and there's flesh. Okay, so who can guess what the skeleton is? Dark matter. Actually, I forgot to say, I like to set a timer, which I'm just starting now, and it's set at 15 minutes, and it'll go off, and when it goes off, someone has to ask a question. Okay? Because I want you all engaged, and you know, you're all here to learn. Many of you have come a long way, right? So listen, right? Because this will be important for your lab as well. You'll need to know this stuff to win the money. Okay. So dark matter halo. And so the flesh is the physics, the galaxies, the baryons, all this sort of stuff. Okay? So let me just review the n-body simulations, which provides the dark matter skeleton on which we're going to build our galaxies. Okay, so we take this, and this is the cosmic microwave background radiation. It tells us something about the very early universe. And we take this, which is the distribution of galaxies in the local universe. This is tracing the local density field. So you can think of this as the very early universe density field. And this is the local universe density field. And we do lots of magic that's been talked about before to get a cosmological model, which is this. And it's a number of parameters fit to very precisely measured data. And it tells us that the universe is, you know, 3/4 dark energy and some dark matter and then a smattering of baryons, okay? So this is how we build our simulation of the universe. We're not doing hydrodynamics here, we're just doing n-body gravity, just gravity, with this cosmological model. And so we don't want this, right? This is not where we're at. Let's get rid of it. There we go. We want this, okay, supercomputer, right? And this is what the Millennium simulation has done, and Bolshoi and so on. Dark matter only, no baryons, no hydrodynamics, no shocks, none of that sort of stuff. We don't want it. Okay, that's how we get our skeleton. And here's just an example of one we run at Swinburne. You know, this is the obligatory movie. Thank you. It's a cosmological volume for the Wiggle-Z Galaxy Dark Energy Survey. That's really not important. You're just seeing what you've seen before in the other simulations. This is the growth of large-scale structure, dark matter, and we've lit up the dark matter here so you can see it. There's no baryons, no galaxies, nothing in here. We want to put the galaxies in post-processing. Okay? So here's how it's done, as Reese has talked about, and as you play with Rockstar. You go in, you find the dark matter halos. So, you know, here's a dark matter halo. And of course, this halo is made up of lots of structure and substructure, so let's break it into the pieces. There's a smooth background, and then there's the substructure. And then what we want to do, there's a lot of information here. Some of these halos may have hundreds of thousands, even millions of dark matter particles. That's a lot of information to carry around. To build the kinds of cosmological galaxy formation models that we're interested in, we don't need to know all that information. What we really need to know is, you know, the mass of this object and its extent, its radius, the angular momentum in this object, for example, the velocity dispersion, the average velocity dispersion. Okay, these are just global properties that, you know, in the large surveys we're measuring the equivalence of. Right? So we don't need to carry around 100,000 particles to quantify this object. We just need to break it down into these properties. So that's all measured. And then you build up the merger tree, and that's what you were building yesterday with Rockstar. And the merger tree basically just tracks the evolution of these properties for a given dark matter halo. That's our skeleton. We don't need all that other information. We just need the key fundamentals. Halo mass, halo radius, velocity, dispersion, and so on. Okay? And so this is from one of Reese's, I believe. And this just shows how a given halo, so this is a halo for a cluster. This is the present day, and this is very early in its life. It just shows how the most massive progenitor grew, and all these things are smaller bits of substructure that merged in to help it grow. Okay? And so we need this to build our galaxy formation model, because presumably, you know, within these dark matter halos, there are galaxies. And so where would galaxies live in the universe? They would live at the bottom of the potential wells. And these potential wells are defined by the dark matter halos. Okay? I just want to make the point that for the cosmological model, the parameters you choose make a big difference to the large-scale structure. So actually, could you just off again, just so we see this? So here, this is from the 90s. No one does this anymore because we have a cosmological model. But if you change, so this is lambda CDM, this is the favored one, and this is redshift 3, redshift 1, and redshift 0. So earlier, more recent, and today. And how structure looks different at different times as the universe evolves. Just dark matter. But if we just go to a standard dark matter cosmology, or a tau cold dark matter, so this is a warm, hot, dark, a cold, hot dark matter cosmology. I'm not going to define what all these are, but just different assumptions about the cosmological parameters, or an open cold dark matter model, so the universe is open. Right. You can see that when you change those assumptions, the large-scale structure changes dramatically. Okay? Both in its evolution and at a given time, they will look different. This is our universe here, of course. But if you put galaxies into these different universes, you'll get different answers. If you're then going to use those galaxies to compare to the real universe, you'll have different answers, okay? So it's important to get that cosmological model right. Just want to make the point that the parameters matter in a big way. Okay. All right. So let's talk about the physics now, or the phenomenology that we use to characterize galaxy evolution, okay, the flesh. All right, so why do we care about galaxies? Okay, so highly nonlinear evolution, right? A given galaxy has a trajectory in time that takes it in weird places, right? And then when you look at a population of galaxies, they go all over the place. It's very interesting diversity of the galaxy population at any given time and across the trajectories of galaxies. They're the home of a lot of interesting internal phenomena. So supernova feedback and star formation, active black holes, supermassive black holes, neutron stars, all this kind of stuff is insanely interesting to study. And then not only that, but they're shaped by their external influences as well. So galaxies collide, they smash together, they run past each other. The large-scale tidal fields may influence their evolution in some way. Okay, so there's a lot of information in galaxies themselves that we want to study. So let me briefly step through some different aspects of a galaxy that I'll break it down, the different parts that are important. And then what I'm going to do is I'm going to switch over to the iPad because there's no blackboard, unfortunately. And I'm going to walk you through a sort of a schematic of how you would build a galaxy. So important for galaxies, right? So obviously star formation. If you're not forming stars, you don't have a galaxy because galaxies are made of stars. That's how you see them. At least that's how you see them mostly in the optical. Okay? So star formation is very important. Now, we can characterize the star formation. So this is a UV image, actually, which highlights all the star formation in M31. When we go and measure this globally across the galaxy and measure the surface density of stars and the surface density of star formation, Kennecott found, so you won't be able to read these axes here, but this axis here is the surface density of star formation, and this is the surface density of gas, basically, divided by dynamical time. And we find this very strong correlation, which tells us that if we know the surface density of gas and the dynamical time of the system, we can estimate what the star formation rate would be. And this would be useful when we build galaxies, because we don't know what the star formation rate is to build our galaxies. That's one of the things that we have to put into our model. So simple phenomenology here. There's no physics in this per se, but simple phenomenology based on what's measured observationally. So supernova feedback, actually maybe you want to get the lights for a couple of these slides because they're quite nice. So supernova feedback, I'm hoping you can see the red. Can you see the red here? All right, so this is gas from the galaxy that's been blown out from supernova that have gone off. So when a cloud of gas collapses, there's a spectrum of masses of stars that are born in that cloud. And the ones that are very massive have very short lives. You know, what is it? Live fast, die young, or something like that. That's what they do. Yeah, right? That's what they do, and they go bang, right? And they throw in lots of energy back out, and this energy takes gas with it and throws it out. So we need to model this in our galaxy formation model, okay? Because this turns out to be very important to the gas cycle. So you know, we look for correlations there. So this plot here is showing how much gas gets thrown out from supernova feedback in units of the star formation rate, because the star formation rate is what's driving the supernova. So if there's 1 unit of star formation, and says 1 up here, that means there's 1 unit of gas mass that's been thrown out because of that 1 unit of star formation that's formed, as a function of the circular velocity of the disk of the galaxy. And you can see that there's not really a great correlation, unlike the star formation. Okay? So not well-constrained phenomenology. So we're going to have to think about what to put in there, or try a couple of different ways to do it. Satellite galaxies. So I showed you the substructure before in a dark matter halo. There'll be galaxies in there. And what happens to those galaxies as they fall into a denser medium typically, especially in clusters full of hot gas, which means the gas that the satellite galaxy is carrying can get stripped off. And that's important because to form stars, you need gas. And if that gas is getting stripped off, then you've got a method to stop star formation in certain objects. And that may be important for the colors and the luminosities of those galaxies if we want to mimic the real universe. So we have to model that. The morphological evolution of galaxies are important. Galaxies smash together. They do all sorts of dynamical things in their morphologies. Their shapes change with time. You may have a merger of 2 objects, which forms an elliptical galaxy. But then subsequent gas accretion might reform a disk. So the morphology doesn't just go from disk to elliptical, or spiral to elliptical. It could go spiral, elliptical, spiral again. Okay. So assembly, especially very massive galaxies, they assemble quite late. To understand this growth, that when there are multiple mergers of massive galaxies, and low mass galaxies as well, these things will grow, and we need to have that in our model. And death, right? So galaxies die, okay? And the exact cause is still not totally known. We believe that supermassive black holes play a role in this. Certainly you can build models where the phenomenology, so having a phenomenology that kills a galaxy that's tied to supermassive black holes works and can match many of the observations. But that doesn't tell you that's exactly what's happening. So there's a lot of research in this area at the moment trying to drill down to what actually kills off galaxies. But we need to put this into our models because otherwise our models will just live forever, almost forever, and that's not what the universe looks like. Black holes need to be in there, of course. There's some nice phenomenology with black hole masses and the bulge mass. So this plot here shows, again, you can't read the labels, but this is the black hole mass here. And this is the bulge mass, so the central round part of a galaxy. And you can see that if you plot one against the other, you get this quite a strong correlation, the black hole bulge relation. So we can use this information when we build our galaxies to infer what a black hole mass might be. So black holes are often not dormant. They become active when there's gas in the vicinity. Supermassive black holes become very active. They produce jets and winds. So here's an example in Virgo of a massive jet coming out of the central supermassive black hole. Here are some examples. So these are, I think these are X-ray images with radio contours over the top. And so the galaxy is down in the center. This is quite a large extent. And here's all the gas around it, gas. And what's happening is that the black hole bubbles into that hot gas. So it's a lower luminosity activity from the central supermassive black hole, unlike this, which is much more energetic. And we might want to reproduce those different stages of black hole evolution if they're important for galaxy evolution. All right, and so here's an example, just a mosaic of observed galaxies. I mean, you've seen this before, right? Of the diversity of the population. So this is what we're really aiming for when we build a galaxy formation model. We have to get the statistics of this right if we're going to be able to use this to understand different questions that we might pose. And I notice we have 28 seconds to the first question, so I'm going to stop there and let's ask a question. I normally have chocolates that I hand out, but I wasn't able to make it to the supermarket today. I'll pick someone. Yeah.
I have a question. Sorry if you mentioned this or are going to. So you're simulating the dark matter. You're assuming that the gas just follows the dark matter.
Yep.
How exactly do you do that? You just assume that the gas density is X percentage of the dark matter?
Yeah, I'll show that in a minute. Actually, that's the next thing I'm going to show. Okay. But it's done analytically. And it's one of the strengths of the model because you can switch from numerical, equation solving to very simple analytic equation solving. Means you can do things really quick. Okay, so I'll do that now. This was my reminder to switch over to the iPad, just in case I didn't notice. So, yeah, this is where I needed a blackboard, because a blackboard would be great. And I've never used an iPad in this way before, so I'm hoping it won't go too badly. But we'll see. And what I want to do here, what I want to do now is just build up a schematic, and I'm going to take your input on this. Okay, I'm going to take your input on this, on how to build up a galaxy formation model. Okay, so let me start by telling you that there are different reservoirs of mass that are important for a galaxy. So can someone name me a reservoir of mass? And let's exclude dark matter for the moment. That's kind of a given. Yep. Okay, can we break it up by temperature to make it even more simple? Great. Make it more simple than that and just have hot and cold. All right, so let's see how this works. So there's going to be our hot. Oops. There's going to be our cold, and let's label it as such. Hot gas. Oops. And let's call this cold gas. Okay, good. All right, so what else? Someone from over here. Stars. We don't have a galaxy if we don't have stars. Oops. So let's do that. So we're going to link these in a minute. So let's just put this one here. Stars. Okay. This is where the old analog blackboard does a good job. All right. Can you see that? Okay, and it didn't save, of course. All right. Cold and stars. All right, what else? Hot. Is that all that makes a galaxy and its environment? And we're thinking here, we can think a little bit more broadly if we want. I mean, obviously the hot gas is not part of the galaxy itself, but it's very important for its evolution. Metals. Let's include metals. Let's say that the gas and stellar components have a component of metals. Yeah, but that's critical for many things. Yep. So black hole mass is good. Satellites will be stars and cold gas. That will be their own. stars and cold gas. But black holes is good. Black holes are good. Okay, so let me arrange these. Hot gas, cold gas, stars, black hole. And let me just go out of this so it saves in case the whole thing decides to die again. You have a whiteboard. Analog. All right. Unfortunately, the people over here won't be able to see. So is there anything else? So I would call that a process that happens. If we're just talking about mass reservoirs, yeah, but we're going to come to that next. Yeah, yeah. Yeah, I'm just worried that it'll just keep crashing and.
Yeah.
Right. Warm? Let's keep it simple. Okay, let's keep it simple. Yeah. Let's leave it at that. We can actually break the gas up into many different temperature phases. Yeah, it is. We don't include it at the moment. Well, the IGA, we include hot gas and cold gas. We do. So we include hot gas and cold gas. Okay, so hot gas is gas that's outside the galaxy, that's at a hotter temperature. Then there's a transition where we transfer gas from hot to cold, and then there's cold gas. We don't track how much mass is in that transition. We just do the calculation and move the gas around. So it is kind of accounted for already. Dust. Yeah, dust will be important for luminosities. So I'm just going to stick with this for now. Okay, so enough to get us started in a model. Will everyone be able to see this? So we have, I'm a bit worried when not everyone will be able to see it. So we have hot, we have cold, we have, is everyone going to see? Yeah. I need to write big though as well. Cold. We have stars. We have black hole. Okay, so let's start linking these up. All right, to build a simple model. We can refine it later and add new components that we think are important. One of the questions you ask models is how simple can I make it and still match certain observations? There's no point in just arbitrarily adding everything you can think of. There's, as you can imagine, there's going to be a lot of interdependency between the different components and the parameters and so on. So you do want to try and keep it simple. My guess is people over here can't really see this. You can see it? Okay. So we need to start, right, linking these up. So firstly, let's imagine that a halo has collapsed and there's also a baryonic reservoir there. So our simulation only tracks the dark matter. Okay, that's all we have. So before stars and gas cools and stars form and all this sort of stuff, how are we going to work out how much hot gas will have collapsed with that halo? Give me a simple equation that will tell me that. An simple analytic equation. So, you know, MV of dark matter has collapsed in the early universe to form a proto-halo. So MV of mass has collapsed in a given time step in the simulation. So if we had to have a stab at how many baryons would be associated with that, what would we say? Yeah, well, baryon fraction. Great, that's exactly what we do. So let's say the infalling gas is just times MV. Okay, so in our simple model here, we have this from the simulation, how much dark matter is associated with that halo, and all the other properties that have been carried through in the merger tree. But we have a row, or a new property for that halo, and it's how much hot gas is there. And at least initially, it's just going to be the baryon fraction times that mass that's there. Everyone agree with that? Okay. So what's going to happen to that hot gas? Okay, have a big halo of hot gas. Maybe in detail it's shocked as stuff's falling in. This is the stuff Mike does and everything. But if we just simple here, that gas is going to cool. Right? So this is where the physics comes in. As it cools, we're going to take it from hot to cold, because that's what cooling means. So let's draw a line. Okay? And the physics is some model that does that. So let me just write cooling. Right? Because that model is not something I want to write up on this board. But you can think of a lot of different models that would deal with hydrostatic, hot halo in hydrostatic equilibrium with some density profile that's going to cool on some time scale or something, and you can actually work out a cooling rate. And so Ed Birchinger and others have done this in the 80s, assuming isothermal spheres and so on. There's simple analytic solutions to this kind of stuff. There are more complicated solutions. You can run simulations and just fit to that under a variety of parameters to say if the halo is of this mass or this redshift or these conditions or this temperature or something like that, the cooling will behave in a certain way. Metals, someone mentioned metals. Metals will aid in cooling. So later, when we form stars, we'll form metals. So we'll want a component in here that tells us how many metals have been thrown back out, and that's going to change the cooling rate. Okay. All right. So what's going to happen to that gas as it cools, though? It will form a disk. It will. Let's assume it conserves angular momentum. It's a fair enough assumption. So now we have a cold disk of gas. Okay. What's going to happen to the gas then? It's going to the gas disk will contract or fragment. And what usually happens when gas fragments like that? Star formation. So going to form stars. So now we can connect this. And do we know of any simple phenomenology that tells us if we have a certain amount of cold gas and we can get the extent of that gas assuming some conservation between the angular momentum in the halo and the angular momentum that that disk, the gas that's cooling would have? So we can get an extent. We know the dynamical time of the system from the halo, taken from the simulation. So we have some information about, the reasonable where this cold gas might be in terms of its parameter properties. Do we know of any simple prescriptions, maybe guided through observations, that tells us how many stars form, given the mass of cold gas and the time scale? The Jeans mass? No. Has a name. So when we have a certain amount of star formation, that will have an IMF. Okay, but I'm just asking, is there a way we can work out how many stars form given a certain amount of mass in a disk? Kennecott law. So I showed this before. Correlation between the cold gas divided by the dynamical time and the star formation rate. And we know the cold gas mass because we have a cooling model that tells us per unit time how much gas cooled. So we have that. We can infer a dynamical time from the dynamical time of the halo. Okay, so we have the Kennecott Schmidt law. And that just says that star formation rate is proportional to the cold gas mass by the dynamical time. Okay. So you see how we're building up this model here? This is observations. This is just analytic theory. We agree we can refine this to more components, but we agree these are the dominant baryonic reservoirs, at least in a simple model. Okay, so now we have stars. Now we have to assume an IMF. All right, and that's useful because there will be supernova, and we also need to know what the luminosities, colors, and so on of the populations of stars that would have formed from that star formation event were. Okay, so there you just pick your favorite. So just to clarify what the IMF is, it's not the International Monetary Fund. Okay, so if you go to any hospital and you go and you stand outside might be a little bit suspect, but you measure the length of all the babies that are born, right, over a month. Okay, if you're not arrested, all right, you can plot a distribution of the length versus the number. Okay, that's the initial length function. Okay, now if you weighed them, if you were able to get in and actually weigh them before you got caught, all right, that would be the initial mass function of the initial weight function of babies. And so it's the same for stars. When gas clouds collapse and they fragment due to turbulence and all the ugly stuff that nobody really understands, there's a spectrum of masses of stars that are formed in amongst that. And it's usually some kind of power law. And the things that are very massive are quite rare, but they have short lives and they explode. And so if you want to know supernova feedback, if you want to have a model for that, you have to assume an IMF, because you need to know how many of those massive things there were in proportion to the other things, the other kinds of stars. So that's what the IMF is. All right, so I just said it. The next step will be that stars will explode. Okay? And so what will that do in this diagram? If we're going to put that effect onto this diagram, what will it do? Can anyone tell me? It will do this, something like, so, potentially. We'll take some of, well, we don't even really want that, right? It will take some of this cold gas and it will eject it out into the hot reservoir, supernova. So now we have to decide what, right? So how do we build a model for supernova? And I actually showed a plot showing that the mass loading, so the mass loading is just how much mass is ejected from supernova due to supernova in units of the star formation rate. So as a function of the size of the disk. And I showed you there was really no correlation there. But it was a number somewhere between 0 and 5, which is actually quite amazing, right? That 5 times the mass of what's formed in stars can actually be thrown out, of cold gas, can be thrown out of the galaxy. Now that's kind of, most semi-analytic models actually need those kinds of numbers in order to work, interestingly, which, as you'll find, try to match higher redshift. But, yep.
Do you find that the mass loading depends on the galaxy size?
Yeah, so people now have started to assume this. What I showed, the observations I showed, were from 1999 by Crystal Martin. I'm not sure if there's a better analysis, a more recent analysis. I think the consensus is the mass loading is somewhere between 1 and 2, somewhere around there. I'm not sure if it depends on size of the galaxy or whatever, but this may be something you want to explore.
Actually, there's a lot of new data on this, and a really good summary is in Crystal Martin's talk, but also lots of other talks at a conference that HiPACC just co-sponsored at Irvine in June called the Baryon Cycle Conference, and almost all of the talks are on the web.
Yeah, so I don't remember if they're...
So there's now a wide range of galaxies. Yes, the mass loading does seem to be dependent on galaxy properties and star formation rates as well as masses and stuff like that.
Yeah, so you can explore that with this kind of model. So you can say, let me just say that delta M cold, so the amount of cold gas we send back to the hot, is equal to some parameter, gamma times star formation rate. Right? So this would just be a constant. And let's just say, let's just try a model where it's 1. It's simple. And we see what that does. And we run that model, and we get an answer, and we say, that answer is total crap. Let's make 2. Right? What's that going to do? It's going to blow more cold gas out. And so what effect will that have if you're blowing twice as much cold gas out? It'll affect the star formation rate. So what will that affect? The supernova rate. Because the supernova rate depends on the star formation rate. So you can see how there's an interdependency between the different physics, the way we set the different parameters, and this is where it starts to get complicated. And this is the point Risa was making, that really to make, these models get much more complicated than this, and they're not that easy to write up. But we're needing these Monte Carlo Markov chain type tools to explore the parameter space in some robust way, because these interdependencies become really hard to sort of work through, to sort out. But anyway, keep it simple. Instead of a constant one here, we can make this a function of some property of the galaxy, maybe the disk. So we could say this gamma, instead of it being gamma, it's gamma equals gamma. So this is a constant now times some power, right? So we could make this model. We could try this model. And depending on how we set this normalization and this alpha, the power, will mean more gas or less gas is thrown out depending on the circular velocity. So you might argue that low mass galaxies, small disks, it's very easy to throw gas out from supernova because the potential is shallower. Right? And then what's that going to have an effect on? The evolution of low mass galaxies. And just to complicate things, it will also have an effect on the evolution of high mass galaxies because high mass galaxies grow from low mass galaxies. Both the accretion of low mass galaxies and they themselves were once a low mass galaxy. So you can see these are the kinds of things we can test. And then we need the observations to try and constrain what the functional forms of these things are. But where we don't have that, we just have to do something that's plausible. All right, so I'm going to say that this is our basic model, the simplest schematic that you can make for galaxy formation. So what we don't have here is the black holes. Okay, so why would black holes be important in picture? Because we have gas, we're forming stars. We're going to have a model here. You'll see it when you look at the code, when galaxies merge together. So halos merge together. The halo trees track that. So when halos merge together, then we can have a simple prescription to say how galaxies would then behave given that situation. We could do a Fermat dynamical friction argument to say they're going to spiral and merge on some time scale, track that time scale in the code, and then make them merge. And if the merger ratio is greater than some amount, then everything becomes an elliptical example. And then we can track that for every galaxy and build up the morphological evolution. Okay? So I don't have that up here, but that's included. But in terms of black holes, what effect is the black hole? Why are black holes now included in models? The AGN feedback. So it's another feedback mechanism. So let me just tell you historically, and I might switch back to my laptop. So historically, people worked really hard to try and get the stellar mass function to look reasonable. All right. So I'll come to that in a minute. Maybe we can just move this now. I don't think we need that anymore. All right, so here are the, what time am I meant to finish, Joel? 12:30?
12:30, but then 10 minutes for discussion.
Okay. All right, so, here's sort of the schema that most semianalytic models use. And I'll come to black holes in a second and show you why that's necessary. But again, we have the main reservoirs. We usually add another reservoir of ejected gas. Gas that's just thrown way out of the potential. And we actually need this because a lot of the gas doesn't come into play in terms of the galaxy evolution because it's been thrown out. Only at much later times does that gas come back in. And then it influences the late stage evolution of a galaxy. But this is basically it. So the baryonic reservoirs and the arrows are the physics, phenomenology. That's where the physics happens and how you transfer mass between these reservoirs. Okay? All right, so we take something like this, the Millennium simulation, okay, and we have code, which you'll be using tomorrow, loads in the trees that describe these dark matter halos, starts at high redshift when each halo first forms, follows them down, and does exactly what's on this board. Oh, this is redshift 12. This is the mass of the halo at redshift 12. Hence, here's a new property for that halo. It's called hot gas. That hot gas is equal to 0.15, whatever the baryon fraction is now, times that mass. Now we have a massive hot gas. The halo might be 10 to the 8 solar masses, so hence the massive hot gas is 10 to the 7, whatever. Okay? We have a cooling model. So we have a new column now, cold gas. Work out how much of that hot gas gets moved into the cold gas. And it's accounting. I've always had the dream of running a semi-analytic model on Excel. Because basically, I think you could just load this in and just have equations that transfer between columns based on the simple physics, the simple phenomenology, and it would do the same thing. Yep?
So a lot of these things run on very different timescales. How do you deal with that?
Yeah, so the trees typically are output on some fixed time grid, which may be irregular. The unfortunate thing is that the time resolution of most simulations is pretty poor. Millennium simulation, it's on average between 250 and 350 million years. So what we... 3 times better, still pretty poor. Okay. So what we tend to do is break it up into sub-steps. So we'll say that the halo has grown this much.
Actually, we stored even time steps in scale factor, which is a lot more time steps when things are happening.
Yeah.
Early time, so it's a little better.
Yeah, so it's a little better. But we break it into sub-time steps. And so we'll say, you know, this is the total amount of baryons that came into the system during this time interval, because this is how much the halo grew. And now let's break that into 10 or 20 sub-time steps, and we'll do all these on those sub-time steps. So we'll add 1/20th of that to the galaxy, do the cooling, star formation, feedback, blah, 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 add the next 1/20th, and so on. So we get a little better. But if you want the UV and everything, so you need, you know, star formation on, you know, 1 million year timescales, it gets challenging. Yeah, you need to interpolate. And building SEDs is tough, you know, and there are assumptions that are made, because you have to. All right, so that's what we do. So we run the trees, and so we get something. So just to remind you, the trees and the physics, and let me say physics like this, physics, all right? And we run that on those trees, and then we get galaxies coming out, and this is what you're going to get. You're going to get these, all right? So this is one particular model that we published in 2006. You can zoom in on this supercluster, not just look at the halos now, but look at the galaxies that these particular assumptions produced. Now, of course, this model has been calibrated with the parameters, again, some parameters, so it looks like the data. But, you know, this is a BCG. There's a massive, so the color coding here is the color of the galaxy based on the luminosity, which is based on the star formation history and the metallicity history. These are just Broussard-Charlot models. That's a particular kind of stellar population model. So model upon model upon model is what you have to do. And then all the satellites around in this massive cluster. And then we can look at the statistics. So this is the galaxy clustering for this particular model, the spatial distribution of galaxies. Does it look like the real universe at redshift 0? Here is the luminosity function in the K-band. So this model, so this I said before, AGN feedback. Why do we include AGN feedback? What was happening prior to the inclusion of supermassive black holes in AGN feedback is they were trying to get this exponential cutoff in the luminosity function. And even though it looks simple, it's insanely difficult to do, right? You'd think it was easy, right? But it's just not. What they were trying to do, so what's the other main feedback mechanism in the model that we talked about? Right? It's supernova. That's the other big feedback mechanism. And so what people were trying to do was increase the supernova feedback. So what does that do? That blows out some of the cold gas, which suppresses star formation. And to reduce the abundance of these very bright galaxies, you need to suppress star formation. You need to stop stars forming in them. Okay? And they could never get it quite right. It always ate away at the knee here, and it was really hard to do. You could kind of get it. The success was claimed, but everybody snickered, you know. And so, and why, right? Because they suppressed star formation with a mechanism that required star formation to work, right? So you can see you start chasing your tail. So what's the attraction in AGN feedback then? That it doesn't depend on star formation. It's an independent mechanism that primarily happens in massive galaxies, because that's where we see these active black holes in massive galaxies. And so that's what we did. That's what we did in mid-2000s, right? We added these black holes, the supermassive black holes in. We had a simple prescription that said, under these conditions, the black hole turns on. It's a new feedback mechanism. Sorry, guys, you can't see this. It was different in that it didn't take the cold gas and blow it out. It acted here. It acted here in the cooling. It stopped gas getting in. So same effect, but acting differently. And stopping gas getting in turns out to be another very efficient way of suppressing star formation, because the galaxy itself quickly uses up the cold gas that it has, and then there's nothing to replenish it. And so that's what the AGN feedback does, and that's why it's become so popular. Now, does that mean that that's what's happening in the real universe? No. Just because we can do it in the model doesn't mean it's really what's happening. But it's an indication of where we need to look and what we need to peer at more closely and dig deeper at observationally in order to understand the physical processes. And it would be a little surprising if we saw all these AGN happening in exactly the right place and it wasn't having some effect like this. So it has to be a player. All right, so galaxy colors and so on. So this model looks impressive, but don't be impressed, right, at all, because we calibrated the model to look like this. Okay, so this is our starting point, not our ending point. What we take home from this are the physical consequences of what we had to do. So it's not that we got a match, but what did we have to do to get that match? And so I've just described with the AGN. So this line here, this line over here, is the same model, but I've just turned off the AGN feedback. No AGN feedback. So cooling just happens. Whenever the halo grows, cooling happens. Right? Cold gas reservoir fills up, stars form, galaxies get brighter. Okay? When I turn it on, that goes away. Supermassive black holes are only really present in terms of, their influence, or they only really get massive enough for this to become efficient in these massive halos. So it doesn't really happen. Supernova really doesn't play much of a role down in the low mass end. They're there. There's probably a little bit, but they don't switch on there. And observationally, we don't see them really switched on there. On the other hand, supernova here is having a dramatic effect. Okay, so this model here has AGN and supernova switched off, I forgot to say. Right? So supernova takes the low mass end and suppresses star formation. It takes this cold gas, pushes it back out to the hot halo, or even can blow it all the way out of the halo itself. So it doesn't even contribute to cooling. And as I said, the supernova is not really important in very high mass halos. The potentials are too deep. There's not enough energy to blow this gas out efficiently. Right? So there's two regimes, and that's how you get the turnover. Okay, so that's what we did. Right? And so it's a kind of a compelling argument, very simple, but kind of a compelling argument to think that the broad picture of building galaxies is something similar to this. All right. And just to highlight that these are different physical phenomena. So they make predictions, right? That the supernova depends on the star formation rate, and the black hole mass depends on, in the way we implemented it, it depends on, AGN feedback depends on the black hole mass and some measure of the velocity dispersion or the mass of the system. So here it's sigma cubed. So it makes a prediction, so it's testable. Okay. I'll just do a couple more slides and we'll stop and we'll go through the other stuff tomorrow. But I just want to make the point here, and this point was made by Risa, I think, of halo growth. So this is a plot of the mass of a dark matter halo in the simulation against the redshift. So these are trajectories of the mean growth histories of halos that end up at a given mass. So Milky Way is what, 10 to the 12 solar masses-ish? Okay. So according to the Millennium simulation, this is the mean growth history of such halos. Okay, and so you can say, okay, so then on average at redshift 3, well, let's say redshift 4.5, the Milky Way might have been 10 to the 11 solar masses. That's kind of how it grows. However, it can be a little deceptive because within that mean behavior, there's a huge scatter of histories. And this is one of the powerful things of these kinds of semi-analytic models, because all these histories are taken into account. So here I've just plotted individual halo growth tracks now for halos that end up at around 10 to the 13.5 solar masses. Now, you can kind of break these. So this is the luminosity function again, and supernova feedback is affecting the low mass end, and AGN feedback is affecting the high mass end. And you can kind of break this up into mass regimes, right? You can say that when halos are down here, when they're low mass, supernova feedback is what's dominating. Okay? This is what happens. Supernova feedback is most efficient when the halos are low mass because the potential shallower. There's a fixed amount of energy per unit supernova, so that fixed amount of energy has more impact when the halos are low mass. So this is the regime where supernova dominate. Once the halo grows above, let's say, up here to the high mass, this is the AGN regime. This is where the AGN feedback dominates and becomes efficient, most efficient. And that suppresses star formation in these high mass systems. And as Risa explained, in the middle there's kind of a sweet spot where star formation is maximally efficient. Neither effect is dominating, right? And that's where the Milky Way appears to be right now. Where a halo crosses these lines and when it moves through this band, makes a difference to its properties, to its evolution. And so that's the point of showing these trajectories, that some of these halos cross up into this AGN feedback regime quite early in their life. And so what's going to happen to them? That AGN feedback is going to suppress star formation and turn them red very early. Right? But in halos of the same mass, there are many whose galaxies won't cross that threshold until very late. Right? So semi-analytics will capture nicely the diversity of when these effects become important for individual galaxies, and that diversity will be reflected in the population you get back out of the model, which makes it a very powerful tool. There is.
How close does your fiducial model look like that schematic plot? And in particular, how sharp is that transition at the mass event?
Yeah.
Does it really look anything like that?
Well, so we'll talk about this tomorrow. I can hold off. It depends on, it's how you implemented it, which depends on the black hole mass and the velocity dispersion. So it's when those two things come together, that's when it becomes important. So on average, it's roughly around this point. But for a given halo, even on a given trajectory, it can be different depending on the merger history. So I'll talk about that. But it's not too bad. It's not too bad. And I can look at the quenching. I can look.
It's not too bad. You mean it's sharp?
It's about up to 1 dex wide. No, that's too large. Maybe half a dex wide. If I look at the quenching mass, and by quenching mass, I'm saying the halo mass at which these things come together to stop star formation. It's very constant with redshift, and maybe has half a dex scatter, roughly, on average. So it's moderately sharp and doesn't seem to evolve strongly with redshift, which is why when I cartoon this up, I just draw a line. Yeah. But the model might, because as we'll find out, high redshift is not well represented in the model. So that might be a reflection that we're doing something incorrectly. Even though we can get it looking reasonable at redshift 0, high redshift's wrong. And that's one of the things that we investigate when we play with these models. And so it's almost 12:30. So I might just stop there and see if there are any last questions. We're 1 minute off a question. So we can take that right now. Does anyone have a last question? Some maybe nugget of information that might allow you to snare a gift? Anything greater than redshift 0. So it depends on what you're looking at. Every model breaks down at any redshift, depending on how close you look at it. Because as you can see, this is a toy model, right? This is not a detailed model that's going to describe shock fronts in merging systems of 10 to the whatever, you know, I mean. So what we're looking for here are global behaviors that we can imprint onto the dark matter evolution to see which properties of the galaxies are least sensitive to all those unfortunate details. And there are statistics and observations which are sensitive to those details, and we'll never match those. For the stellar mass functions we've been talking about, so these global statistics, redshift 1's not too bad. Once we get above redshift 1, I think the models all struggle. Although we can get reasonable models, right? So we can do it. And so you'll see, we'll see tomorrow. You can do it. It requires more thought, much more thought than just the simple model that I've outlined here. So are there any more questions? Yep.
Do you do anything special after a merger or during a merger?
Yeah, during a merger there's a starburst. Essentially that the starburst, how many stars form during that merger is dependent on the mass ratio of the galaxies merging, obviously. The higher the mass ratio, or the closer in mass the two galaxies are, the more effective it's going to be at turning the cold gas into stars. And then the mass of cold gas is the other thing that's important. So if there's no cold gas, of course, there's going to be no stars. So these are called dry mergers, right? So the more cold gas there, the more likely you are to have a big burst.
But you might clarify, one of the big differences in different semi-analytic models these days is whether there's also, in addition to the starburst, an AGN phenomenon, a quasar, that blows out the gas and quickly terminates star formation. As I recall, you don't put that in.
It's not needed.
Rachel Somerville does.
Doesn't make a difference.
Yeah, the model results aren't that different as long as you're not actually looking at the AGN luminosity.
Yeah, so that's important for the AGN property, for the black hole and AGN properties. And it's not that much different for a very simple reason that's understandable, is that when halos are growing in this growth phase, baryons are coming in, right? And you could blow out all the baryons at redshift 3, and at redshift 2.8, that and more have already come back. So if you want that to be effective, you have to blow them out, and then you have to blow out everything that's going to come in the next giga year or 2 or 3 giga years, and then you start wondering whether that even makes sense physically. Although it may. There have been some models. Evans Skanapenko has a model that pushes gas out and stuff like that. But yeah, I mean, and these are the kinds of games that you can play. If you can only fit the data with some model like that, then maybe you want to make a prediction and go and see if the observers can find a way to test that. Or maybe your model's just wrong. Right? So that's the game you play to try and learn something. And this is why, as Risa said, the questions you ask are really important. They have to be very well constrained and suited to the method that you're using. All right, shall we call that lunch?